Hello everyone, good morning or good evening, depending on your time zone. I'm Riccardo Buscicchio, a third year PhD student at the University of Birmingham in the UK. Let me thank, first of all, the organizer for giving me the opportunity to present the work of my group to such a wide community, and specifically given the current circumstances. Now, in the next 10 minutes or so, I'd like to talk to you about satellite galaxies of the Milky Way. And more specifically, I will try to convince you that LISA will be able to detect gravitational waves, gravitational wave sources within those satellites, and possibly also to discover new ones, to discover new satellites, depending on their properties, of course. Using the binary white dwarfs as tracers. The work I'm going to present is the product of many people's effort. All of them are listed here. You can see those names, and they are either former or current members of my institution. Now, the original idea, as unraveled while we developed it, into two companion papers. Both are part, of course, of a broader and longer ongoing research activity in our department. The first of the two papers, led by Valeriya Korol, has used a population synthesis code to characterize the observability scenarios of interesting binary white dwarf systems. The second, which is the one I'll focus mostly in this talk, was performing a detailed Bayesian analysis, Bayesian inference, on a simulated LISA mission in order to infer on the detectability and on the parameter properties of these systems, of these binary white dwarf systems. So the purpose of these two papers has been then to use specifically realistic candidates for these satellites, using information from direct observation of those, and at the same time using realistic mission simulation and specification in order to characterize in a robust manner the observability of these systems. The first few minutes I'll spend will be trying to introduce a little bit the paper on the population synthesis. Now, as you can see here, there are many plots. Some of them, well, all of them are from the paper, and you'll find much better description in the paper itself. So I invite you to read it. It's in the title if you want to check it out. There are a few information which I'd like you to keep in mind while we progress through the rest of the talk, and well, basically what I'd like you to keep in mind is the fact that star formation history and stellar mass are the dominant features for the detectability of sources within those satellites. More specifically, as you can see here, for 5 examples which are captured in this table, even if the distance is quite relevant, of course, for detectability because of the SNR, the mass, the stellar mass, of course, convoluted with specific metallicity, with specific mass transfer models, and convoluted with a specific star formation history, will provide different numbers for the number of sources that you expect to detect. Now, this column here is showing the number of expected sources from for example, from the Magellanic Clouds and from these other 3 satellites, which are somewhat good candidates for different reasons. You'll see that in a second once we go through the rest of the talk. But here, I just want you to keep in mind that we are talking about tens of sources for the clouds, maybe if you're like even hundreds for the Large Magellanic Cloud over a longer mission. But at the same time, I would like you to keep in mind that This is strongly dependent on the specific feature of the satellite itself. Now, this paper has explored in greater detail all the possibilities, and I think it has captured quite in a clear manner what are the dominant features and what are the subdominant features. For example, the metallicity or the mass transfer model itself of the binary companions. Now, going straight to the Bayesian inference, which is what I would like to cover. Actually, before we go on, let me mention that Valeriya will probably cover part of this content also during his invited talk on Thursday, when she will give an overview of the current status, current knowledge of the galactic binaries. So I strongly encourage you to attend the talk, because I'm sure you will learn many things. And going back to the Bayesian inference, the second paper that we published has been covering the parameter estimation. We have been considering many possible configurations. Again, we've used realistic observations, real observations of satellite galaxies. As you see here, there are approximately 60 dots or stars, and there are 5 specific circles. Now, the circles are just showing you the 5 candidates that we used as a comparison among the 2 papers, while the stars are representing detected sources at the specific frequency, at the specific inclination and masses of the companion within a specific satellite, while dots are representing undetected sources. The blue shading is describing the sky uncertainty of sources detected within it, while the red shading is capturing the foreground, which is going to be important if we actually want to associate a specific source to the satellite, therefore distinguishing it from the foreground of binary white dwarfs from our own galaxy. So, of course, this behavior is quite strongly dependent on the frequency and on the inclination and on the masses of the source, of course, on the distance itself of the satellites. And here in the following slide, I'm going to give you just a rough, very, very brief overview of the overall behavior. Now, as you see here, we are considering 3 different frequencies among the columns, and we are also increasing the masses among the columns. And as you can see, we basically go from a sky which is almost completely dark with respect to the to sources from the satellites at low frequencies with low masses and with all edge-on sources, which is a somewhat artificial scenario, to a very bright sky where basically we can detect a single source from every single satellite that we know so far of. And that, of course, there are intermediate behaviors, but overall that's the only features I would like you to keep in mind while we go through to the rest of the talk and the discussion, of course. So that's the feature I want you to keep in mind. At the same time, if you just want to consider a single satellite, which is basically covering the entire behavior, I would suggest to follow Fornax, because as you can see, you have to keep in mind that Fornax is sitting at 139, if I'm correct, 139 kiloparsec from us. So let me actually check that. Sorry. Yeah. And as you can see, yes, so it's 139, and for that reason, it's actually just a little bit far away with respect to the horizon sensitivity, at least at those frequencies, which is somewhere around 120. For that reason, depending on the specific mass that you choose and the frequency that you choose, you might expect to see or not see sources from within it. An interesting feature of Fornax is the fact that it's sitting in a region which is very depleted from foreground sources. Therefore, once you have detection, you might be able to actually infer its association with Fornax pretty easily. That becomes even easier with the small Magellanic Cloud and the large Magellanic Cloud, just because they are very far away from the disk, where the density of foreground sources is, of course, much, much bigger. Sagittarius is instead a somewhat strange candidate, just because it's over its entire extension in the sky. There are regions which are at higher density of foreground sources and regions which are at lower densities of foreground sources. Therefore, actually, depending on the specific placement of the source within the satellites, you might have different results. But on overall, it is interesting the fact that we can actually move very close to disk, or in some scenarios we can even see through the disk, just because the dust extinction is, of course, completely suppressed, because we are not talking anymore about electromagnetic sources. At the same time, we have the problem of the foreground. So, depending on the scenarios, we might be able to detect or not sources. Going on, I've already told you what we expect from the specific candidates, but one feature we have not discussed is the actual location of the sky and the lower limit on the distance, or in general the inference on the distance. Now, this is quite an important feature, just because if you are of course, if you increase the frequency, you are capable of inferring better and better the location of the sky of the source, and at the same time you can infer you can place a lower limit on the distance. Now, if this lower limit is, for example, taken across a population of detected sources, you might consider, for example, doing a population inference, so selecting a bunch of sources and associating them with either a known or an unknown galaxy, just because they are coherently spreading their uncertainties over the same region of the distance posterior, while at the same time you might also use other features of the sources, which is basically the chirping behavior. That's because, we'll see actually that in a moment. Let me actually point out that the discovery, as a rule of thumb, if you want to keep that in mind, the discovery or association with a new host, with a new satellite galaxy, will be possible, for example, with the galaxy somewhat similar to the Large Magellanic Cloud, in an optimistic star formation history, and in a region somewhat close to us, say for example at 50 kiloparsecs. Of course, again, this is just a rule of thumb. If you want to explore the overall behavior, you probably want to check out the paper and have a read at it in detail. But keep in mind that 100 sources from such satellite will appear as a 1.5 excess just by doing simple Poisson counting. Again, as I've said, a more refined approach where you don't just do the counting, but you actually do a population inference, so take a bunch of sources and infer the location, might give you better results, might give you better constraints on the position of those sources and the eventual associated host. As I was mentioning before, there is another bonus feature, which is the chirping sources. For those sources, here I've just taken from the paper a reference value, we have quite good error bars on the frequency derivative, and of course depending on the SNR. But in general, if you have a non-negligible frequency derivative, and if you assume, which is of course something debatable, a gravitational wave driven shrink of the orbit, you might expect you might be able to infer even better the distance, just because you independently infer the mass, and therefore you can decouple the mass from the distance in the parameter estimation. Once you get that, you have a much better constraint on the distance, and therefore you might be able to really locate with exquisite measure the sources. Now let me just say that probably we can have all the discussion you want, and I'm happy to answer questions now. And thanks again for having me on this talk.